Does gravity travel instantly, or is it bound to the same cosmic speed limit as light? We watch planets orbit smoothly, perfectly, as if they're locked into real-time gravitational communication, reacting with no delay at all. And for centuries, scientists assumed exactly that. Gravity acts instantly, infinite and immediate, stretching across space faster than anything we could ever measure. It felt intuitive, almost obvious. If the sun tugged on Earth, the response seemed immediate. No waiting, no lag, just a constant invisible pull. And yet beneath that simplicity lurked a problem, because instant gravity would break causality, break physics, break everything we think we know about how signals move through the universe. So here's where the tension sharpens. What if the universe doesn't allow instant action at all? And what if one person came along who dared to question it? A man who reshaped reality itself. That's where Einstein steps in next. Einstein didn't start with gravity. He started with speed. The speed of light, to be exact. He proposed something radical. Nothing in the universe, not mass, not sound, not information, not even gravity, could outrun light. That idea wasn't just bold. It was almost offensive to classical physics. If gravity was truly instantaneous, it would be the one thing in the cosmos exempt from this universal speed limit. So suddenly, a mystery opened like a crack through reality. Could gravity be slowed down to the pace of light itself? Einstein wasn't satisfied with the old picture of forces acting across space like invisible strings. He looked deeper. He asked stranger questions. He imagined space not as empty nothing, but as a fabric, a thing that can bend, stretch, twist. And more than that, he fused space with time itself. To Einstein, the universe was no longer a stage. It was a flexible structure, dynamic and alive, capable of shaping the motion of everything inside it. This is where tension begins to tighten. Gravity, in Einstein's mind, wasn't a force at all. It wasn't something reaching across black space to tug planets into orbit. Instead, objects move the way they do because space-time curves around them. A planet orbits the sun for the same reason a marble circles the center of a warped trampoline. Not because the sun is pulling it, but because space-time slopes downward around it, and the planet simply rolls along the curve. Suddenly, the universe isn't being held together by instantaneous threads. It's flowing along invisible valleys in space-time. That single idea shattered centuries of assumptions. Newton's force became Einstein's curvature. A pull became a ripple. And in that moment, the universe changed shape, literally. But here comes the real twist. If gravity is curvature, then what happens when the curvature changes? Everything with mass warps space-time. A star moves. A black hole merges. Two neutron stars spiral inward. These aren't silent events. They deform the fabric beneath them. And if space is a fabric, any sudden change must ripple outward. Slowly, instantly, at light speed. Einstein leaned over his desk, his equations swirling with geometry instead of force. And he found an answer hidden in the math. If mass shifts, space-time doesn't update everywhere at once. Like a drumhead struck at one point, the impact spreads outward as waves. Not sound waves. Not electromagnetic waves. But gravitational waves. Ripples in reality itself. Imagine that for a moment. Gravity might move. It might radiate. It might escape a black hole merger and sweep across galaxies like a shockwave. And if that's true, we're left with a burning question. How quickly do those ripples travel? If the sun could vanish and space-time rippled outward instead of responding instantly, Earth wouldn't just fall out of orbit. We might feel those ripples crest over us like a delayed cosmic earthquake. Einstein predicted something astonishing. Those waves should move at the speed of light, no faster, no slower. But believing that was one thing, proving it was another. For decades, physicists hunted for gravitational waves like ghost signals, like whispers in the dark. They built detectors. They listened to stars. They waited for the universe to move. Because only by catching those ripples could we answer the mystery that started it all. Does gravity really obey the cosmic speed limit? If we could detect gravitational waves and measure how fast they travel, we'd finally know whether Einstein was right or wrong. And science doesn't hinge on belief, it hinges on proof. So here's the hook that drags us forward. If space-time bends, how fast does that bend propagate across the universe? Is gravity chained to the speed of light, or does it outrun it in silence? Faster than signals, faster than photons, faster even than causality should allow. Our next step is into the realm of cosmic signals, where gravitational disturbances might announce themselves across billions of light years like ripples on a dark sea, waiting for us to hear them. When you think about gravity, you might picture it like an invisible tether, steady, constant, unbroken, linking planets to stars and galaxies to one another. But what if gravity isn't a silent, continuous pull at all? What if gravity can send signals? This is the mystery we face next. If the sun shifts in space, does Earth feel that change instantly? Or does gravity have to tell us that something moved? If gravity were static and unchanging, nothing would have to travel. But if gravity can change, if it reacts dynamically to motion and mass, then something must carry that information outward. And here's the crack that widens. Does gravity broadcast updates the way light does, as radiation moving at a finite speed? Or is it more like a still pond, where motion is felt everywhere at once? Nature rarely chooses the easy answer, and this question pushes us toward deeper waters. Because imagine the universe not as empty void, but as a calm surface of water, perfectly still until something disturbs it. When a pebble hits a lake, ripples expand outward, each wave carrying news. Something just happened here. Mass in the universe may behave the same way. A star wobbles. Two black holes spiral together. A neutron star collapses. Those movements aren't quiet, not in Einstein's universe. They would ripple through space-time just as waves ripple across water. The curvature changes, and like shock spreading from an impact, that curvature must travel. Not instantly, not infinitely fast. It must move, ripple, propagate. And this idea flips gravity on its head. No longer a static force, but a dynamic field. No longer a fixed pull, but a shifting, trembling fabric that can vibrate. And if that's true, then every massive event in the cosmos, a supernova explosion, a black hole swallowing a star whole, galaxies colliding, could send gravitational signals across. Unimaginable distances. Signals we might detect. Signals we might measure. Signals that could finally tell us the speed at which gravity travels. But here lies the tension that gripped physicists for decades. If these ripples exist, why can't we see them the way we see light? Light radiates in waves, electromagnetic and bright, but gravitational ripples would be astonishingly faint. They wouldn't shine. They wouldn't glow. They wouldn't light up the sky. They'd stretch and squeeze space itself, invisibly, quietly, subtly, like the softest tremor in a vast ocean. So the mystery deepens. If gravity sends ripples, how do we detect something so delicate, so slight, so cosmically gentle? For most of human history, we couldn't. We could only theorize. We could guess. We could calculate and hope the universe would one day speak loudly enough to be heard. And for the longest time, those gravitational waves were nothing more than mathematical whispers in Einstein's equations, predicted but unseen. A rumor inside spacetime. But science doesn't rest on rumors. It waits, it builds, it listens. A century after Einstein first proposed the idea, humanity finally built instruments sensitive enough to catch the faint trembling of reality. LIGO, a machine capable of detecting distortions smaller than a proton. And this is where the gravitational ocean we imagined stops being metaphor and becomes real. Because those ripples, if they exist, don't just tell us gravity moves. They tell us how fast it moves. They're the universe's Morse code, tapped out across billions of years. And if we can decode those signals, we solve one of physics' oldest riddles. Which brings us to the next turning point, the moment scientists finally caught one of these ripples in the act. The moment theory became evidence. The moment gravity spoke and humanity heard it. The era of gravitational waves was about to begin. For nearly a century, gravitational waves lived only on paper. Numbers in Einstein's notebook, chalk on blackboards, whispers of curvature rippling through spacetime that nobody could touch, see, or confirm. Einstein himself doubted they could ever be detected. If the universe were a pond, the waves were so subtle they barely wrinkled its surface. Scientists searched anyway. They stared into the cosmos, hoping for proof, not light, not sound, but a shiver in reality itself. Nothing came. Observatories listened for decades, like detectives chasing a rumor, waiting for spacetime to tremble loud enough to register. Instruments improved, but still, silence. No ripples, no confirmation, just an unanswered question hovering over everything. Do gravitational waves actually exist, or are they just beautiful math? The mystery deepened as technology raced forward, and yet the universe remained stubbornly quiet. But science thrives under pressure. Experiments grew larger, more ambitious. Minds pushed boundaries. The world needed something colossal, something violent enough to shake the cosmic fabric itself. And so, humanity built LIGO, the Laser Interferometer Gravitational Wave Observatory. Two enormous L-shaped machines stretching kilometers long, so sensitive they could detect a ripple in spacetime smaller than the width of an atom. Inside those long vacuum-sealed tunnels, laser beams bounced between mirrors, perfectly aligned, waiting for the day when spacetime would stretch or compress ever so slightly, when a gravitational wave would pass through and reveal itself. LIGO was more than a telescope. It was an ear pressed against the universe, listening for tremors from unimaginable distances. Every adjustment to its machinery was like tuning an instrument to pick up the faintest cosmic music. And for years, the only thing it heard was noise. But the belief held. Somewhere out there, black holes collided, stars collapsed, neutron cores spiraled inward, events brutal enough to send waves racing across the cosmos. If relativity was correct, those waves were coming. We simply had to wait. Then, on September 14th, 2015, spacetime finally spoke. LIGO detected a tiny distortion, barely perceptible yet unmistakably real. Two black holes over 1 billion light-years away had collided, merging into one even more massive, more terrifying singularity. The impact was so intense it shook spacetime like a drum. The waves spread outward, passing through galaxies, crossing cosmic voids, skimming dust clouds, and drifting invisibly across the Milky Way until they reached Earth, where LIGO's lasers trembled in response. Humanity had captured a ripple in reality itself, not light, not particles, gravity. in motion. It was Einstein's prediction brought to life, a century-old theory finally proven by the universe. But detection brought more than confirmation. It brought data. If gravitational waves traveled slower or faster than expected, if they lagged behind light or outran it, we would see it in the timing. LIGO didn't just hear the waves. It recorded when they arrived at each detector, allowing physicists to measure their speed across Earth with astonishing precision. For the first time in history, we had the means to test one of the universe's most fundamental questions. Not with theory, but with evidence. How fast do gravitational waves travel? And if waves carry changes in gravity, then the answer would reveal the true speed of gravity itself. So now the mystery sharpens into its next form. Armed with detection, with real ripples crossing space-time, scientists turned to the most critical task of all, measuring how fast those ripples moved. Because if gravity's waves traveled no faster than light, Einstein was right. If they arrived early, gravity could be faster, perhaps instantaneous. If they lagged, physics might need rewriting. The stopwatch had begun. Next, we step into the test itself, the experiment that timed the heartbeat of the universe. When that first gravitational wave washed across Earth, it didn't just shake LIGO's mirrors, it shook the foundations of physics. 2 detectors, one in Louisiana and one in Washington, separated by thousands of kilometers, felt the universe quiver, almost at the same instant. The question now was razor sharp. How fast did that ripple travel between them? If there was even the slightest measurable delay, it could rewrite what we believe about space-time. Scientists held their breath. They ran calculations. They compared timestamps down to microseconds. They accounted for noise, for seismic rumble, for every terrestrial vibration that could muddy the signal. The stakes were enormous. This wasn't just about the wave itself. It was about the speed at which reality updates. If gravitational waves had arrived noticeably early, gravity might outrun light. If late, perhaps it lagged behind light-speed signals. But the data slowly, carefully, resolved like a photograph sharpening into focus, and what it revealed was nothing short of historic. The waves reached the first detector, then the second, separated only by the time it takes light to cross that same distance through Earth. There was no suspicious lead, no cosmic jump ahead of photons, no instantaneous response unfolding across the globe. Instead, gravitational waves behaved exactly like a messenger traveling with the universe's universal speed limit, the speed of light. Even more astonishing, later detections confirmed it again and again across different wave events. Black holes merging, neutron stars colliding, space-time ringing like a struck bell. Each time, the arrival pattern matched what light would do. Einstein's prediction, dismissed by some as mere theory for 100 years, was now backed by hard measurement. Gravity does not leap across space in an instant. It moves, it travels, it ripples outward. And it does so at light speed, no faster, no slower. But this wasn't just a number on a chart. This meant causality held firm. This meant information cannot outrun the universe's limit. Gravity behaves like light not just in speed, but in principle. It carries information, and that information cannot travel instantaneously. A star explodes, a black hole merges, a galaxy trembles, and the universe takes its time relaying the news. Reality communicates with a finite rhythm. Not infinite, not immediate. There's a cosmic tempo, and gravity keeps perfect time with photons. Scientists watched the data align with theory so precisely it was almost poetic. A ripple in space-time and a flash of light from a neutron star merger arrived together, separated only by the smallest fraction of a second. billions of years of travel, yet synchronized as if scripted. If gravity moved faster than light, those ripples would have arrived first. If slower, light would sprint ahead. But no, they raced neck and neck, confirming that gravity, like light, obeys the universal limit. And that should settle everything, shouldn't it? But science never stops at should, because for all the precision, all the verification, one unsettling question lingers like a shadow behind the data. Is this always true? What about situations more extreme than any we've measured? At the edge of black holes, at the beginning of the universe, or deep within theoretical realms where space-time tears and folds? LIGO proved how gravity behaves here, in the detectable cosmos we can observe. But what if somewhere out there, in environments we cannot test, gravity bends the rules? That possibility is where this story shifts direction, into alternate realities, into hypothetical universes where gravity might act without delay. Because if gravity were instantaneous, even in theory, our solar system should behave differently. Orbits would destabilize. Cause could outrun effect. Physics itself would unravel. Yet the planets move calmly, harmoniously, meaning gravity cannot be instant. But let's explore what would happen if it were. Next, we're stepping into a hypothetical world where gravity ignores distance, where the sun's pull reaches Earth instantly, and everything we know threatens to collapse. What if gravity did act instantly? What if the force holding Earth in orbit wasn't bound by light speed, but instead stretched across space with no delay at all? An immediate tether between masses regardless of distance? At first glance, that might sound simpler, even elegant. No waiting for signals, no propagation, just raw influence. But peel back that simplicity and something deeply unsettling appears. Right now, it takes light 8 minutes to reach Earth from the sun. That means if the sun magically disappeared, not physically possible, but hypothetically, we wouldn't know immediately. We would orbit for 8 whole minutes before darkness arrived. But if gravity were instantaneous, Earth should feel the sun vanish before the light fades. Gravity would have to update faster than light, faster than causality, faster than reality permits. And that idea, strange as it is, becomes even stranger when we reverse it. Right now, Earth doesn't orbit where the sun was 8 minutes ago. It orbits where the sun is now, because the curvature of space-time guides it smoothly, consistently, without violent corrections or sudden changes in direction. If gravity were instant, Earth would constantly adjust to a position that no longer exists. The orbit would spiral, misalign, destabilize, tearing the solar system into chaos. Imagine planets yanked toward past positions like dancers chasing a partner who already moved. Jupiter dragged toward where the sun was moments before, Saturn lagging further behind, Neptune trailing like a misaligned cog in a broken machine. Their orbits would twist into elliptical messes, and within millions of years, perhaps less, the solar system would unravel. Moons would break free. Planets could sling into interstellar darkness. Stars in galaxies would no longer follow smooth curves. They would tug toward ghosts of mass positions, collapsing spirals, dissolving cosmic order. The universe would not look the way it does. It could not function the way it does. Order would give way to entropy, structure to turbulence. Yet, we observe stable systems everywhere. Solar systems, star clusters, spiral galaxies gliding through space like clockwork. Their harmony alone argues against instantaneous gravity. Something is smoothing the chaos, and the reason is profound. Gravity is not a force dragging planets behind delayed positions. Planets follow space-time itself. Instead of being pulled toward where the sun was, Earth moves along the curve created by where the Sun is now, because space-time curvature moves with mass at a finite, consistent speed. No ghost pulling, no memory gap. Orbits remain stable because they don't require instant updates. Space-time simply bends, flows, evolves. And everything follows naturally. Instant gravity would create contradictions, effects preceding causes, signals traveling backward through logic, information leapfrogging light across the cosmos. If gravity acted infinitely fast, a change in one location would be felt everywhere at once. The universe would be wired like a perfect telepathic network, violating relativity at its core. We could send information faster than light. We could break causality. We could, in principle, create time paradoxes where the effect arrives before the cause. Physics, the very thing that allows stars, planets, people, would fracture. But relativity slams a door shut on that nightmare. Einstein's universe forbids instantaneous influence because instantaneous influence would dismantle time itself. Light speed isn't just a number. It's a boundary woven into the fabric of existence. Gravity obeys that boundary, not because the universe is limiting it, but because the universe is built from it. Space-time is not static, not frozen, not instantaneous. It's dynamic and causal. Every curve, every ripple, every gravitational touch arrives on delay, predictable, measurable, finite. And this leads us to an even deeper question. Is the speed limit a rule for convenience, or a safeguard protecting reality from collapsing into paradox? If gravity cannot exceed light because causality would fall apart, then we've only scratched the surface. Because now we must ask, what happens to causality if gravity tries to cheat that limit? Could faster-than-light gravity tear holes in time? Our next step takes us directly into that danger zone, where cause and effect strain against one another, where faster-than-light influence creates time loops, contradictions, impossible sequences. If gravity were instant, causality in the cosmos would break. And that is exactly where we're headed next. Causality. Cause leads to effect. Action precedes reaction. It's so deeply woven into reality that we rarely question it. You flip a switch, then the light turns on. You drop a cup, then it shatters. But allow gravity to move faster than light, to transmit information instantly, and that logical sequence begins to unravel. The universe would no longer be a clean chain of events, but a tangled loop where the future could influence the past. If one observer could use gravity to signal another faster than light, and that second observer used the same trick to respond, relativity predicts something bizarre. The reply could arrive before the original message was ever sent. You could warn yourself not to send the message, and if you listened, the message would never be sent. Yet the warning still arrived. A paradox, tight and venomous, like a snake eating its own tail. The universe, logical, ordered, precious, collapses under contradictions. But this isn't just philosophical hand-waving. Physics lives or dies by consistency. Faster-than-light gravity would let us rewrite cause and effect, scramble timelines, allow events with no origin. It would be like deleting a memory that still happened. Picture a spaceship that could modulate gravity to send a message instantly. A simple ping. A ripple telling another ship light years away, I'm here. If gravity outruns light, the receiver gets the signal immediately. No delay. Now, spin the frame of reference. Relativity allows observers moving at different velocities to disagree about the order of events. To one, the signal was sent first. To another, the reply arrives first. And if both use instant gravity, you could create a closed loop, an outcome with no beginning. A ship could receive a distress call from itself before the disaster ever happened, rescue itself from a future accident, or worse, cause one. Such timelines aren't just strange, they are impossible under every law we trust. Physics protects causality the way a firewall protects a network, by banning any mechanism that lets information exceed light speed. And gravity, tied to spacetime, must follow those rules. The speed of causality is the speed of light. Gravity doesn't just follow it, gravity is built from it. And yet, nature loves loopholes. Because here's the twist: quantum physics. Down at the smallest scales, where particles flicker in and out of existence, where uncertainty rules, where observation changes outcomes, something strange happens. Two entangled particles separated by galaxies seem to affect each other instantly. Touch one, and the other reacts with no measurable delay, no light speed limitation, no waiting for gravitational curvature to propagate. Instant correlation. It looks like faster than light information. It looks like causality breaking. It looks like the thing relativity forbids, happening anyway. Einstein himself hated it, calling it spooky action at a distance. And though entanglement never allows usable information to travel faster than light, the mere existence of instant correlation feels like a crack in causality's armor, a tiny opening, a whisper. What if gravity has a quantum side too? So now tension rises again. The universe is classical at large scales and quantum at small ones. Gravity follows relativity, entanglement defies intuition, and we have no unified theory to stitch them together. The mystery grows teeth. Is space-time truly limited to light speed propagation because reality demands causal order? Or could gravity, if fundamentally quantum, behave differently under extreme conditions? Could gravitons, hypothetical quantum particles of gravity, reveal behaviors relativity can't account for? Every answer leads to deeper questions. And that brings us to the next unexplored territory, the uneasy intersection of Einstein's smooth spacetime and quantum physics' chaotic probabilities. If gravity must obey causality and quantum entanglement seems to ignore it, then the next segment asks a question that scientists still wrestle with today. What if gravity is quantum in nature? General relativity describes the cosmos like a smooth, continuous fabric, elegant, geometric, curving under mass and energy. Quantum mechanics, on the other hand, paints the universe as jittering, discontinuous, granular, a storm of probabilities rather than a calm sheet of space-time. These two pillars of physics stand side by side like monuments, each powerful, each proven, yet fundamentally refusing to merge. And so we face a new mystery. What if gravity itself is quantum? If space-time is made not of smooth curves but of tiny vibrating units, something like atoms of geometry, then the force of gravity might not be a continuous bend at all. It could be carried by particles, just as electricity is carried by photons. Physicists even have a name for that hypothetical quantum of gravity, the graviton. If gravitons exist, they would be massless, flitting through space-time at, yes, the speed of light. They would carry gravitational influence one interaction at a time, transmitting curvature the same way photons transmit electromagnetic waves. Relativity predicts gravitational waves propagate at the cosmic speed limit, and quantum theory agrees. Gravitons, like photons, should travel at c. So the two theories, enemies everywhere else, shake hands here. Both insist gravity cannot be instantaneous, but the handshake is brittle. Because relativity and quantum mechanics, when pushed into extreme environments, tear apart like mismatched gears. Near a black hole, quantum fields rage in ways Einstein never imagined. At the dawn of the universe, space-time density approaches infinity. Quantum behavior explodes, and GR collapses into singularity. The equations diverge. The universe glitches. We don't know which theory yields and which prevails. Or if a deeper theory waits beyond both. If gravitons are real, they must move with finite speed. But if space-time itself breaks down into quantum foam, boiling with wormholes, fluctuations, uncertainty, then what does speed even mean at that scale? Time itself becomes fuzzy. Distance dissolves. The speed limit may be defined only for smooth classical spacetime, a rule that might not apply where spacetime is no longer smooth. Suddenly, the question isn't just about how fast gravity travels, but whether the concept of speed survives at the Planck scale. Consider the moment two black holes spiral toward collision. Their masses distort spacetime so violently that quantum and relativistic descriptions both strain to describe what's happening. The ripples we detect, gravitational waves, follow light speed as they sweep across the universe. But what about the ripples near the singularity, deep inside the gravity well where quantum uncertainty reigns? What if gravitons inside that extreme zone don't behave like waves traveling through classical space? What if information there moves differently, not through space, but by reshaping it? A graviton, in theory, could tunnel, like particles do. It could jump through space-time foam in ways our equations can barely outline. The cosmic speed limit might hold everywhere we can observe, yet break quietly where we cannot. Invisible, untestable, possible. Tension builds because we have no experimental window into quantum gravity. We can detect gravitational waves across galaxies, but we cannot measure what happens near a singularity. We can describe gravitons mathematically, but we cannot isolate or detect one. We can model spacetime warping smoothly, but when that warp becomes infinitely steep, our laws stop working. We are staring at a locked door, and behind it lie answers that could reshape physics. Maybe gravity always travels at light speed, even at quantum scales. But maybe, under unimaginably extreme conditions, exceptions emerge. Maybe the universe hides scenarios where gravity shortcuts through warped geometry, bypasses classical distance, or alters causality in microscopic bursts too small to violate the macroscopic order we observe. And if quantum gravity is strange, if relativity bends, cracks, or loops at its limits, then we must look directly at the places where gravity becomes strongest. The places where space-time is no longer a calm fabric, but a storm. Black holes, gravity so intense it traps even light, curvature so steep it nearly tears space-time. If anything reveals cracks in the speed limit, it will be there, where relativity and quantum physics collide and refuse to agree. So the next question draws us toward the edge of the cosmic abyss. If gravity follows light speed everywhere we've measured, what happens in zones where gravity is unimaginably strong? At the edge of a black hole, the universe changes personality. Space stretches, time slows. Light itself, that tireless, undefeated mariner of the cosmos, begins to curve inward like a river pulled toward a drain. This is a place where gravity stops being gentle guidance and becomes raw authority. Stars that wander too close fall like pebbles into a well with no bottom. Even information strains to escape and fails. And here's the mystery that physicists wrestle with. Every day, what happens to gravity here, where space-time bends harder than anywhere else? If gravity is the curvature of space-time, then a black hole is the ultimate sculptor, twisting the cosmic fabric until it folds like paper and plunges into darkness. The closer you move toward its horizon, that invisible rim where escape becomes impossible, the stranger reality behaves. Seconds stretch into centuries, distances shrink, directions blur, and through all this distortion, gravity continues to operate, guiding matter into spirals of unimaginable violence. But pause on the paradox. Even here, as space-time warps into a funnel, relativity insists that gravitational effects still propagate at the speed of light. If a black hole's mass shifts, if it merges with another, if it devours a star, if its rotation changes, that shift doesn't update everywhere at once. Instead, gravitational waves ripple outward like shock waves from an impact, spreading at c, the universal limit. Even near the most extreme gravitational objects in existence, nothing jumps ahead. No instant updates, no faster-than-light corrections. Black holes may twist the geometry of space, but they don't override the speed of propagation. The curvature itself travels outward, rhythmic and finite. The event doesn't synchronize across the cosmos instantly. A collision here sends a signal outward, but it travels like everything else, step by step, light speed precise. And yet, tension simmers beneath that certainty, because theory meets a wall when we push deeper. Outside the event horizon, we can describe everything. Space-time curves, waves propagate, signals move outward. But cross the threshold, and the universe refuses to answer. Inside the horizon, gravity doesn't just dominate, it reigns absolutely. No light escapes to carry information out. No particle can flee to tell the tale. Our equations begin to crack. Our assumptions falter. General relativity describes the exterior elegantly, but the interior? There, we enter a realm where classical space-time loses definition. Clocks break. Causal order twists. Density climbs toward infinity. We know gravity still propagates at c outside the horizon. But what about inside? Does gravity behave differently where space collapses inward faster than signals can escape? Does the wavefront stall? Does propagation cease to matter entirely when every path leads to the singularity? Picture this strange scenario. Two objects fall into a black hole, one slightly behind the other. Does the second object feel the gravitational pull of the first? Does that information propagate through the collapsing geometry at light speed? Or does everything inside simply follow a single pathway? A one-way descent into timelessness? Where gravity is no longer communication but geometry consuming itself. This is not a question we can test in a lab or observe through telescopes. We cannot place instruments inside an event horizon. We cannot extract data. We cannot even be sure our models apply. To understand gravity here, we walk blind, guided only by math and imagination. And imagine further. If gravity is space-time curvature, and space-time collapses inward infinitely, then propagation may not behave the same way we observe outside. Light speed might hold, or collapse, or become meaningless. In the external universe, gravity respects causality, respects the cosmic limit. But inside, the rules we know may dissolve. Relativity predicts its own breakdown at the singularity, like a bridge ending in fog. Something new is needed, something beyond Einstein. And that leads to a deeper possibility. Maybe gravity does not simply curve space-time. Maybe it interacts with dimensions we cannot see. Maybe its behavior near the horizon hints at a structure larger than the 3D world we inhabit. Which brings us to the next frontier: theoretical frameworks where space-time extends beyond the familiar, where gravity may leak, slip, or spread into extra dimensions. If relativity rules our visible universe, could gravity behave differently beyond it? Inside a black hole, we cross a threshold where certainty dies. Physics, confident, logical, beautifully predictive beyond measure, begins to unravel like a thread pulled too far. Outside the event horizon, we can track gravity. We can measure wave speeds. We can watch space-time flex and ripple. But once past that boundary, once even light surrenders, our equations stop answering. Here's the mystery. Does gravity behave differently inside a black hole? Does it still propagate at light speed when space itself collapses faster than escape allows? Does propagation even mean anything when every direction leads inward? The event horizon marks not just a border in space, it marks the border of knowledge. Every theory we trust, every test we've done, every confirmation LIGO has delivered, all applies to the outside. But inside, we're blind. We don't know whether space-time waves ripple there. We don't know if gravity travels at sea, stalls, fractures, or becomes something else entirely. In here, Einstein's smooth geometry twists into something jagged. Time doesn't flow, it falls. Space doesn't curve, it caves inward toward a point of infinite density where the laws of physics tear themselves apart. And that point, the singularity, is the most terrifying place science can imagine. Not because it's violent or destructive, but because it defies comprehension. In a singularity, space-time ceases to have meaning. Distances shrink toward zero. Density explodes toward infinity. Causality, that sacred order we've fought so hard to protect, may disintegrate. If you could stand inside, you can't, but imagine the thought experiment. There might be no speed limit at all, or no speed to measure, because time is no longer a dimension that flows. Gravity may not travel. It may simply be everywhere inside at once, like the entire interior is already collapsed into one point. Or perhaps gravity becomes irrelevant, because everything is accelerating toward the singularity with no need for propagation. Our models fail here, not from lack of effort, but because the math itself tears open. General relativity predicts infinity. Quantum theory refuses to allow it. Two great pillars argue, and reality stays silent. Scientists stare into this darkness through equations, simulations, paradoxes. But without data from inside a horizon, we have nothing but theory and imagination. Does gravity propagate inside? Does it remain bound to light speed? Does it collapse with space, fold into quantum structure, fracture like glass under infinite pressure? We simply don't know. We can simulate collapse on supercomputers. We can watch stars torn apart by tidal forces. But no signal has ever emerged from within the horizon to tell us how gravity behaves there. It is the ultimate locked room in the universe, and we're stuck outside, listening to the walls creak. So what do scientists do when the universe gives no answers? They build new ideas. Some propose that inside the event horizon, space-time doesn't simply collapse, it transitions. Maybe the singularity isn't a point, but a tunnel. Maybe gravity distributes through hidden layers of reality we can't perceive. Maybe the interior of a black hole isn't the end of physics. Maybe it's the beginning of new physics. Extra dimensions, quantum foam, holographic mapping, wormhole topology. These aren't science fiction concepts. They're serious frameworks mathematicians develop because the standard model simply cannot survive past the horizon. If gravity behaves strangely inside a black hole, it may be because gravity interacts with something outside our visible dimensions. something beyond width, height, depth, and time. And so, from this darkness emerges our next question. If black holes break our equations, perhaps that means the universe is bigger than 4 dimensions. Perhaps gravity's confusion inside the horizon is a clue, a hint that spacetime is layered, that reality is more than it appears. What if gravity doesn't die inside a black hole, but escapes somewhere else? This is where we turn to the next chapter, the radical possibility that gravity leaks into extra dimensions. What if everything we see, stars, planets, galaxies, even ourselves, exists like ink drawn on the surface of a sheet of paper, while gravity seeps beneath it into a deeper volume we can't perceive? This is the mystery of extra dimensions, not imaginary, but mathematically plausible, physically motivated, and taken seriously by some of the leading theorists alive today. In our everyday experience, we move through 3 dimensions of space and 1 of time. Up, down, left, right, forward, back, and the ticking of moments. But what if those 4 aren't all there is? What if reality branches wider? Some theories propose 5D, others 10D or 11D under string theory. And in those frameworks, gravity is a different kind of citizen than matter, radiation, or light. Instead of being locked to our familiar 3D brain, gravity may roam freely through a much larger bulk. If true, it could explain one of the strangest facts in physics. Gravity is absurdly weak. The electromagnetic force holds atoms together. Nuclear forces bind protons, but gravity barely manages to keep your feet on the floor. A tiny magnet can lift a paperclip against the gravitational pull of the whole Earth. Why is gravity so faint? Why does it seem diluted, thinned, stretched? One elegant possibility: because it isn't confined to our world. Gravity might be weaker simply because it spreads through dimensions we cannot access, like sound leaking through walls into the next room. Imagine a flashlight shining on paper, bright, focused, intense. Now imagine the same light diffusing into open space, weaker, fainter. That's gravity, if brain-world theory is correct. Our observable universe may be just a membrane floating in higher dimensional space. Light and matter are trapped to the brain, like colors on a canvas. But gravity may sink into the extra dimensions like water through fabric. And here's where tension sharpened to a blade's edge. If gravity wanders into unseen dimensions, could it travel differently there? Light is stuck to our brain, forced to obey our speed limit. But gravity might have shortcuts, not faster in the way we think, but traveling through bulk dimensions where distance is warped, folded, compressed. If a gravitational wave could dip into the bulk and re-emerge elsewhere, it might seem to us as if it crossed vast stretches of space faster than light, not breaking the rules, bending around them. Just like a wormhole doesn't make you exceed speed, it shortens the path. In extra-dimensional gravity, speed may be limited, yet routes may differ. Brain-world cosmology imagines our universe as a 3-dimensional surface embedded in a higher dimensional ocean. Gravitons, hypothetical quantum carriers of gravity, might live not just on our brain, but in the bulk. They could skim across it like dolphins traveling beneath the surface while light crawls along the top. This could let massive gravitational influences propagate in bizarre ways. Waves could reflect off higher dimensional structures, amplitude could dilute, energy could leak outward, and yes, path length might shrink. A gravitational disturbance could take a detour through an unseen dimension and reappear ahead of schedule, seeming superluminal from a 3D perspective without ever violating relativity's local speed limit. We're talking about gravity moving not faster, but smarter. Of course, this remains speculation. We have no confirmed evidence of extra dimensions, but we also have no proof they don't exist. String theory, loop quantum gravity, holography, ADS/CFT, all whisper the same audacious hint. Reality may be larger than it looks. If extra dimensions are real, gravity might behave differently near their folds, branes might warp, and space-time could flex in ways we haven't even begun to measure. A black hole could leak gravitational energy into them. Perhaps what we call a singularity isn't compression to a point, but a bridge into the bulk. The inside of a black hole might not be the end of physics. It could be a doorway. And if gravity spreads through these hidden corridors, its apparent weakness becomes a clue, not a flaw, a signature of dimensional richness. And that leads us to an even more provocative thought. If space-time itself can warp, stretch, and twist through hidden geometry, could that warping itself affect how fast gravity's influence appears to travel? Not break the limit, but bend the route. Not outrun light, but outmaneuver it. Under extreme curvature, could space-time fold like origami, allowing gravity to arrive sooner than expected without breaking causality? Could gravitational lensing, wormholes, or brane folds mimic superluminal behavior? This is where our exploration turns next, into the possibility that warping spacetime might alter how gravity moves, not by speeding it up, but by changing the very landscape it travels through. If space were flat and still, movement would be simple, like running across a smooth floor. But space isn't flat. It bends, it stretches, it wrinkles under gravity's weight, like fabric draping over a hidden shape beneath it. And here rises a new mystery. Can the shape of space-time itself change how fast things appear to travel? Not by breaking the cosmic speed limit, but by warping the path itself. Because there's a subtle but profound difference between moving through space and bending space, so the destination comes closer without moving at all. Think of ants walking across a sheet of paper. If the sheet stays flat, they crawl the long way. But fold the paper so two distant points touch, and suddenly the ants don't have to cross the distance. The distance itself disappears. They didn't move faster. The space moved differently. In physics, this is the difference between velocity and geometry. You can't drive faster than the limit, but you can change the road. General relativity doesn't just tell us gravity slows time and curves space. It tells us curvature is dynamic, not static, not fixed. Space can contract. It can stretch. In extreme cases, it can even connect two distant points through warps or tunnels, theoretical constructs like Einstein-Rosen bridges, better known as wormholes. If such structures exist, even briefly, even virtually, they don't let objects exceed the speed of light. Instead, they rearrange space-time so the path itself shrinks. Observers outside might see particles or waves appear to move faster than light, but in truth, light speed remains unbroken. The rules don't change, the map does. And this idea leads to an astonishing possibility. Gravity waves might appear to travel faster depending on how space-time is curved around them. In highly warped regions, near supermassive objects, within cosmic filaments, across expanding voids. Distances may not behave intuitively. Gravitational ripples could take shortcuts through curved geometry, arriving earlier than photons forced to stay on our flatter brane. If this sounds like science fiction, consider how this logic already shows up in observable astronomy. Light does not always travel in straight lines through the universe. It bends, it arcs, it curves around massive objects because space itself is bent by gravity. When we look at distant galaxies, their light sometimes arrives along multiple paths, stretched into rings, mirrored into arcs, magnified by cosmic lenses. This warping doesn't change the speed of light. It changes the distance light must travel. A beam that would take 1 billion years through flat space might reach us sooner because the road bends inward like a valley carved through space-time. No speed law broken, just clever geometry. And here the tension tightens, because if curvature can alter light's path, could it also sculpt gravities? Could a gravitational wave slip through a deeper trench in space-time than photons can access, reaching detectors earlier and giving the illusion of superluminal travel? We haven't caught such an anomaly yet, but in extreme gravitational environments, it's not impossible. Picture two signals leaving a distant cosmic collision. One gravitational, one electromagnetic. Light must weave through warped space, slowed by curvature, detoured by gravity wells, scattered by plasma, delayed by medium. But gravitational waves? They pass through matter almost effortlessly, cutting through galactic cores like wind through fog. If spacetime folds sharply enough, gravitational waves might follow a straighter internal route, crossing a shorter geodesic, even though both obey the same speed limit. Detectors might register them first, not because they outran light, but because they outmaneuvered it. And here we stand, breath held, on the verge of an insight. Speed in the universe is not just velocity, it's topology. How fast something arrives depends on the shape of the path, and gravity shapes that path. The evidence is subtle, indirect, hidden in lensing patterns and delayed gamma bursts from distant mergers. The universe bends itself constantly, sculpting routes through its own geometry. And gravitational lensing, our next stop, is the clearest sign that space is not static, that curvature controls movement, and that speed and path are entwined like strands of the same thread. So now the question becomes sharp and irresistible. If light bends around massive objects, what does gravity do? Does it bend too? Does it follow a different path? And do those paths reveal deeper truths about speed and structure? To answer, we turn to the next observable clue: gravitational lensing, where space-time itself acts like a cosmic magnifying glass. Light is supposed to travel straight, the universe's purest, most disciplined traveler, racing through space at a constant c. Yet when light passes near something massive, a galaxy cluster, a black hole, even a star, it bends. Not because the light itself curves, but because space is curved, and light is merely following the shortest path through that curvature. This is gravitational lensing, one of the most visually arresting proofs that gravity isn't a force pulling across emptiness, it's geometry itself. The cosmos becomes a hall of mirrors. Distant quasars stretch into arcs like wet paint dragged across the sky. Whole galaxies smear into rings. The famous Einstein rings, perfect circles formed when light from a background galaxy is warped around a massive object directly in front of it. We aren't seeing distortions caused by defocused glass. We're seeing space-time flex. The fabric of the universe becomes a lens. Every photograph of a warped galaxy cluster is a message from the universe. Einstein was right. Space-time curves, gravity shapes geometry, and light obeys the terrain beneath it. That's the tension, not poetic, but mathematical. Bent beams confirm that gravity doesn't act instantaneously. It influences space, and light travels through that warped field. If gravity were instant, if curvature updated everywhere at once, lensing would look wrong. Rings would smear incorrectly. Distortions would mismatch mass distribution. But they don't. They match precisely the curvature we expect if gravitational influence propagates at light speed. building geometry dynamically rather than snapping it into place. Light isn't being yanked sideways by a force, it's following the shortest geodesic, the path spacetime lays before it. Gravity doesn't push light, space bends light, and that bending reveals the speed at which gravity sculpts its architecture. Consider the Hubble images of Abell 370, background galaxies stretched into sweeping arcs. The Clash survey, bright rings framed by invisible mass, or the iconic bullet cluster, where light curves around a presence we cannot see. In every case, the lensing patterns match simulations only if gravitational fields expand outward at a finite speed, not instantly. Any delay shorter or longer than c and the arcs misalign. The distortions rupture symmetry. The universe's lensing signatures fall apart. Our telescopes reveal a cosmos behaving like Einstein drew it. Space-time dynamically shaped by mass, updated at light speed, predictable to absurd precision. In a sense, gravitational lensing is a cosmic slow-motion photograph of gravity traveling across time. Light arrives later, traveling through geometry constructed earlier, but never earlier than causality allows. And yet, the universe offers a twist, a complication, a shadow. Because while lensing confirms general relativity's geometry, it also reveals something we never expected. There isn't enough visible matter to produce the curvature we see. Galaxies spin too fast. Clusters lens too strongly. Space-time bends more than visible mass can justify. Something else is pulling. Something that interacts gravitationally, but not electromagnetically. Something invisible, yet undeniable. We call it dark matter, and lensing is how we discovered it. Dark matter bends light more strongly than ordinary matter alone. It shapes gravitational wells we cannot see but can measure through lensing. That means the universe contains massive amounts of unseen gravitating material. And wherever that material lies, space-time curves accordingly. Gravity propagates through these invisible structures, building terrain for light to follow. But here's the enigma. Dark matter doesn't radiate, doesn't shine, doesn't interact with light. Yet it interacts with gravity perfectly. If gravitational influence propagates at light speed, how does that behave when the source of curvature is invisible? Do gravitational waves travel cleanly through dark matter? Do they slow? Do they refract? Does dark matter respond with the same time delay that visible matter observes? Here tension tightens further, because dark matter warps space predictably. But dark energy does something stranger. It stretches space outward, accelerating cosmic expansion. If lensing confirms gravity's classical limits, dark energy challenges them, which means our next step must dig deeper into the shadows, into the unseen force shaping the universe on the largest scales. So the mystery now evolves. If dark matter bends light through gravity at light speed propagation, how does dark energy reshape space-time itself? And does that influence travel at sea as well? Next comes the dark expansion we don't yet understand. Dark energy, and the puzzle of an accelerating universe. Galaxies shouldn't hold together, not the way we see them. Their stars spin too fast, like children clinging to a carousel that's turning far beyond the speed limit. By all Newtonian expectations, these systems should fling themselves apart. The outer stars move so quickly that visible matter, the stuff we can see, touch, count, simply isn't enough to generate the gravity required to keep them bound. Yet, they remain intact, stable, elegant spirals swirling millions of light years wide. Astronomers mapped these rotation curves, expecting a smooth drop-off, slower speeds at greater distances from the galactic core, exactly what visible mass predicts. But the curves flattened instead. Stars far from the center moved just as quickly as those near it. Something unseen must be adding to gravity's pull, forming massive halos around galaxies like ghostly scaffolds. We named that invisible mass dark matter, not because it's ominous, but because it doesn't shine, reflect, or absorb light. It interacts gravitationally, and only gravitationally. The universe is full of it, more of it, in fact, than ordinary matter by a factor of more than 5. Here, the tension tightens. How does invisible mass shape galaxies so precisely? Its gravity behaves identically to ordinary matter, bending spacetime with the familiar strength, the familiar geometry, obeying Einstein's rules. It curves light as if space itself were drawn tighter, and gravitational lensing reveals its hand in the architecture of galaxy clusters. We detect it through gravity alone, through the curvature of spacetime it generates. And crucially, nothing in dark matter's influence shows a lag or delay outside relativity. If dark matter shifted position, lensing and rotational behavior respond in lockstep with general relativity's speed limit. That means dark matter's gravitational influence, mysterious as it is, propagates no faster than light. If gravity traveled instantaneously, dark matter halos would behave strangely. Galaxy rotation would show mismatched timing. Lensing patterns would distort in ways we've never observed. Instead, everything lines up perfectly with gravity that updates across billions of miles at a finite, constant speed. But if dark matter plays by relativity's rules, dark energy seems to break the rhythm. While dark matter binds, dark energy pushes apart. Where dark matter strengthens gravitational wells, dark energy stretches space-time itself, accelerating cosmic expansion in every direction. The faster galaxies move away from each other, the more space expands between them. And unlike dark matter, which clumps into halos and draws matter inward, dark energy behaves like a uniform pressure embedded in the vacuum of space. It doesn't cluster, it doesn't pool, it repels. This difference introduces a new mystery. Does the influence of dark energy propagate the same way gravity does? Or does the expansion of space operate under different rules entirely? If dark matter is the invisible scaffolding holding galaxies together, dark energy is the silent engine pushing them apart. The universe grows faster as it grows older, an astonishing late-time acceleration that stunned cosmologists when first discovered in 1998. Gravity, governed by relativity, should slow expansion. Matter should drag everything inward. But the large-scale structure of the cosmos tells a stranger story. Expansion speeds up, almost as if space-time were inflating from within. And here, questions sharpen like knives. Does dark energy communicate its influence across space? Or is expansion simply a property of the vacuum itself? If dark energy is uniform, omnipresent, tied to the fabric rather than mass within it, then perhaps the concept of speed doesn't apply in the same way. Gravity travels. Expansion happens. That distinction cracks open a new line of tension. If gravity propagates through spacetime, dark energy might instead reshape spacetime. It may not send ripples. It may stretch the cosmic fabric everywhere at once. Or it may spread at a rate governed by the same speed limit, but on scales too vast to measure directly. And this leads us into an even deeper contradiction. Distant galaxies recede from us faster than light, not because they're breaking speed limits, but because space itself expands beneath them. Light speed rules movement through space, not the growth of space itself. So now the universe asks us a sharper question. If dark matter obeys normal relativistic gravity, does dark energy follow the same rules? Or does it play by an entirely different set? The next step is into the accelerating universe, where expansion outruns light not by motion, but by geometry. And we must ask whether speed limits still hold when space itself is moving. Next up, dark energy puzzle. The universe should be slowing down. That's what gravity predicts. Enough time passes, enough mass gathers, and expansion ought to gradually grind to a stop, maybe even reverse into a cosmic collapse. But that's not the story the cosmos tells us. Instead, distant supernovae flicker with a faintness that reveals something astonishing. The universe is accelerating, not decelerating. Galaxies aren't just drifting apart, they're being pushed apart faster and faster as time goes on. Something is driving expansion, stretching space-time itself like a rubber sheet pulled from every edge at once. It isn't matter. It isn't radiation. It isn't gravity as we know it. This mysterious something, invisible, untouchable, unmeasurable except through its effects, is what we call dark energy, and it may be the most perplexing force in the cosmos. The deeper we look, the more unsettling it feels. The expansion isn't slowing, it's speeding up. Space isn't drifting, it's accelerating outward as if fueled by an unseen pressure woven directly into the vacuum. Einstein once introduced a term to model such behavior, the cosmological constant, then famously regretted it. Now, it appears he may have stumbled onto the right idea for the wrong reasons. Here is where the tension sharpens like a blade drawn slow from a sheath. Why is the universe accelerating at all? What mechanism stretches space-time so uniformly, so tirelessly, so relentlessly that even gravity cannot rein it in? We know dark energy makes up roughly 68% of the universe, more than matter, more than radiation, more than all stars combined, yet we cannot detect it directly. It does not clump, it does not pull, it does not shine. Instead, it pushes. Its influence is not like gravity propagating outward from mass. It is something more pervasive, more global, a property of space itself. When space expands, dark energy does not dilute like matter does. Instead, it maintains density. More space means more dark energy, which in turn means faster expansion. It's a feedback loop written into the vacuum. And gravity, for all its dominance on small scales, for all its role in forging stars and galaxies, becomes overwhelmed by this silent, repulsive presence across cosmic distances. But if dark energy works by stretching space, not by pulling through it, a new mystery rises. Does the effect of dark energy propagate, or is it simply there, everywhere at once? When space expands, is that expansion communicated like gravity at light speed? Or does space-time expansion operate outside the usual framework of signal and response? Gravity travels at c, gravitational waves ripple outward at c, curvature updates at c. But dark energy does not radiate. It does not send waves. It does not announce changes the way gravity does. Instead, it behaves as if expansion is a built-in property of space-time. If dark energy changes, if its density shifts, if the cosmological constant varies, how would the universe respond? Would that alteration need to propagate outward at the speed of light, changing expansion gradually? Or would the change manifest everywhere simultaneously, as if part of space-time's underlying code rather than a force moving through it? Here, friction meets flame, because if expansion just happens without propagation, it brushes against causality. Yet observations of cosmic microwave background fluctuations and structure formation imply dark energy behaves in ways compatible with finite light speed influence, even if its effect feels omnipresent. We're left staring at two possibilities, and neither fits perfectly. Either dark energy evolves by sending information through space-time, limited by c, or expansion is not a signal-based process at all, meaning speed may be irrelevant, a category error. In one model, expansion propagates like gravity. In the other, expansion unfolds like the universe rewriting its own metric in real time. Both cannot be entirely right. Both might be incomplete. And here the cosmos whispers a more disturbing possibility. Maybe gravity and dark energy are two sides of the same phenomenon, one curving space inward, one pushing it outward. If dark energy is the negative pressure of vacuum, then expansion might be nothing more than space-time itself responding to a form of gravitational field we barely understand. And if that's true, then the speed question becomes harder. We aren't just measuring how fast gravity travels, but how space-time itself responds to whatever dark energy actually is. If the fabric expands, how quickly does that change ripple across the cosmic web? At light speed or beyond? And if beyond, does it violate relativity or reveal a deeper layer beneath it? Which leads us toward our next question. Because cosmic acceleration forces us into the strangest corner of modern physics. If the universe is stretching faster than light can keep up, galaxies beyond our cosmic horizon slip away forever. Not because they are moving faster than light, but because space between us expands faster than photons can cross it. That doesn't break the rules. It bends the context those rules operate in. Expansion is not motion through space. It's the growth of space. And that means the next challenge sharpens into focus. If galaxies can recede faster than light due to expansion, does gravity weaken or behave differently across those unreachable distances? Next, we step into cosmic scale dynamics, where recession outruns photons, where speed limits blur, and where we ask whether gravity follows or fails when space-time runs away beneath it. Distant galaxies aren't just far, they're running away from us, and the farther they are, the faster they flee. Some retreat at half the speed of light, some nearly match it, and beyond a certain distance, something almost unbelievable happens. They recede faster than light itself, not through motion, not through propulsion, but because the space between us grows. This leads to one of the most counterintuitive truths in cosmology, one that sounds like heresy until you grasp the rules beneath it. Galaxies can disappear past our cosmic horizon, expanding away faster than photons can bridge the gap. We can point a telescope toward them and see ancient light, but never new light. They slip beyond reach, not because they break physics, but because the metric of space-time stretches underneath them. They do not outrun light. The road gets longer beneath their feet. Space expands, and in doing so, carries galaxies outward like driftwood on a swelling tide. No law is violated. Instead, our assumptions about distance collapse into something stranger, more fluid. Here, tension rises like dark energy itself. How can anything recede faster than light if nothing can travel faster than light? The answer lies in context. The speed limit applies to motion through space, not to the expansion of the space itself. Light speed is a local rule, a law for objects moving within space-time, but not a constraint on space-time's own growth. It's like drawing two dots on a balloon and inflating it. The dots don't move, the balloon stretches. Their separation increases not because they travel, but because the surface expands. Now scale that image to the cosmos. Every distant galaxy is painted onto the universe's fabric. As the fabric stretches, distance grows. When expansion outruns photons, we lose contact. Not because the galaxy runs, but because the track beneath it lengthens faster than anything can sprint. We watch light leave, but never catch later waves. The universe becomes a one-way mirror, showing us only the past. This leads to a deeper question. What happens to gravity across those unreachable distances? If space expands faster than light can cross, does gravitational influence stretch too? Does the curvature propagate outward, slowed by the same expansion? Does the wavefront weaken, scatter, or fade into cosmic background? Gravity, like light, travels at sea. But if the space it moves through expands faster, gravitational influence from far-flung galaxies may never reach us. Their pull drifts beyond grasp. Their space-time curvature never arrives. They become gravitational ghosts. Not because their gravity is weak, but because the universe grows too fast for signals to bridge the gap. Gravity doesn't break the limit. The limit outruns gravity. Imagine two galaxies separated by a gulf of expanding space-time. They attempt to influence each other through gravity, through light, through any information at all. But their messages fall short. Their gravitational waves stretch as the cosmos expands beneath them, like ripples pulled thin on a widening lake. Eventually, those waves redshift into silence. Influence fades into nothing. The universe becomes partitioned, islands of causality drifting apart on a sea of expanding geometry. Gravity doesn't fail, but it never arrives. We live in one island, watching others drift beyond reach, vanishing into the accelerating dark. And here the tension twists even tighter. If gravity cannot cross the cosmic horizon, does its strength diminish differently across immense scales? We know general relativity governs galaxies, stars, black holes. But on cosmological distances, assumptions blur. Dark energy pulls space-time outward. Gravity struggles to keep structure intact. Could gravity weaken differently over billions of light years? Could its propagation, delay, produce effects we mistake for new physics? Modified Newtonian dynamics, MOND, and other alternative theories attempt to explain galaxy rotation curves without invoking dark matter, suggesting gravity itself may behave differently at vast distances or extremely low accelerations. Most evidence still supports Einstein, yet mysteries remain. Perhaps gravity subtly shifts behavior in regimes beyond our reach. Perhaps cosmic expansion hides variations we cannot measure. Perhaps the speed at which curvature spreads remains constant, but the landscape it crosses isn't. Which brings us to our next monumental question, one we can't answer with lenses or telescopes alone. If gravity travels at light speed, how do we directly test that propagation across cosmic distances? How do we measure delays in gravitational influence when expansion stretches the path and redshifts the waves? The only way is to observe events powerful enough to shake space-time across billions of light years. Neutron star collisions, black hole mergers, cataclysms bright enough to flash both gravitational waves and electromagnetic signals in synchrony. And so we step into the next chapter. Observational tests designed to time gravity itself across the cosmos. Across a room, gravity feels absolute. Across a solar system, predictable. Across a galaxy, steady and sure. But stretch that distance to billions of light years, across voids wider than imagination, through an expanding cosmic fabric, and a new uncertainty creeps in. Does gravity behave the same at every scale, or does distance change the rules? We assume gravity weakens with separation, like smooth, perfect mathematics, inverse square, elegant, dependable. Yet when astronomers chart the movements of stars in distant galaxies, the behavior refuses to line up. The outer stars move too quickly. Galaxy clusters contain too much unseen mass. Gravitational lensing bends light more strongly than visible matter accounts for. We blame dark matter, a silent, invisible medium filling the universe. But some physicists whisper a different possibility. Maybe gravity itself changes at cosmic distances. Maybe Einstein's law bends subtly, stretching thinner across expanding space, shifting form like a tide drawn across unimaginable scales. This line of thought led to modified Newtonian dynamics, MOND, a radical proposal suggesting that gravity doesn't always follow the inverse square rule. At low accelerations, such as the outer edges of galaxies, gravity might fall off more slowly than expected, offering extra pull without unseen matter. It's bold, controversial. Some rotation curves match it astonishingly well. Others resist. MOND refuses to go quietly, evolving into richer frameworks like TeVis or tensor vector scalar gravity, where extra fields complement spacetime curvature. These models try to do something audacious, explain galaxy behavior without dark matter at all. If correct, they hint that gravity itself morphs across vast distances. Not instantly, not superluminally, but differently. And with that possibility comes a deeper question. Does gravity propagate across intergalactic voids at the same speed and strength we measure locally? Or does expansion dilute its reach? A gravitational wave crossing 1 billion light-years is stretched, wavelength expanded, frequency lowered, power dispersed. We detect it as a faint tremor, a gentle sigh of a collision that once screamed in space-time. Could propagation itself weaken? Could the universe's growth dampen gravity in ways Einstein's equations don't yet capture? This is where tension tightens until it hums. If gravity changes at scale, then every event we measure is also a test. Every black hole merger is an experiment. Every neutron star collision is a stopwatch. We look for timing differences between gravitational waves and light, for arrival patterns that slip even a fraction beyond expectations. If gravity slowed over distance, waves from across the cosmos would lag. If gravity weakened differently, waveforms would distort in ways models cannot predict. If alternative gravity is real, the universe itself is the laboratory. But only if we learn to read its signals. And here lies the next challenge. We need more than 2 detectors, more than LIGO and Virgo, more than a few caught ripples. We need a network, a constellation of observatories able to triangulate waves with precision finer than a hair's breadth across the width of Earth. Imagine timing gravitational waves from mergers occurring billions of light-years away. The further the source, the longer the wave travels, the more cosmic expansion stretches its signal, like music played from a distant valley. If the speed of gravity is perfectly c, no deviation will emerge no matter how far we measure. But if gravity behaves differently over cosmological distances, the signal itself becomes the proof. A merger in a galaxy cluster could arrive nanoseconds off prediction. A neutron star collision could deliver light and gravity slightly out of sync. A structured, repeating anomaly could reveal gravity weakening in ways MOND-like theories anticipate. We are standing at the threshold of these measurements, building machines that listen across the universe like seismographs pressed to cosmic bedrock. So here the hook emerges sharp and irresistible. How do we build experiments that detect tiny deviations in gravity's speed across the universe? How do we stretch our ears to cosmic length and let space-time itself teach us whether gravity ever wavers from light speed propagation? The answer lies in observational power. Next-generation detectors capable not just of catching waves, but of timing them like heartbeat pulses across billions of years. To measure gravity's speed limits, we don't need equations. We need the universe to speak. And that brings us to our next step. Observational tests, where we design experiments to measure gravity's speed with terrifying precision and ask, could the universe reveal a crack we haven't seen yet? How do you measure something that crosses billions of light years? How do you time a tremor in spacetime so faint that it stretches a detector mirror by less than the width of a proton? The question hangs like a blade over modern physics. How can we measure the speed of gravity directly? We can't flip a cosmic switch to trigger gravitational ripples. We can't tap a black hole like a bell. Instead, we must wait for the universe to create experiments for us. Cataclysms so violent they shake spacetime itself. Neutron stars spiraling into collision. Black holes merging into one, collapses that release energy not as light, but as gravitational waves that race across the cosmos. These events are our cosmic clocks, our signal flares, our chance to listen for ripples and light in the same moment and compare arrival times down to the microsecond. But the precision required borders on impossible. It demands machinery so stable that even Earth's vibration threatens to drown the signal. It demands detectors so sensitive they can register motion 1 billion times smaller than an atom. To measure gravity's speed, we must time the universe itself. Enter neutron star mergers, nature's most invaluable laboratories. When two neutron stars collide, the event isn't quiet, it's a symphony. They send out gravitational waves and electromagnetic radiation, gamma bursts, X-rays, radio echoes, all emerging from the same cosmic heartbeat. If gravity were faster than light, the waves would arrive first. If slower, they would lag. Instead, when LIGO captured such an event in 2017, GW 170817, the gravitational wave and gamma flash reached us just 1.7 seconds apart, after traveling nearly 140 million light-years. That delay wasn't due to speed, it was due to the messy physics of the explosion, where light took time to burst free from the debris. When corrected, the result was extraordinary. Gravity and light traveled side by side for 10 to the 15th seconds, matching to better than 1 part in a quadrillion. The universe tested Einstein for us, and gravity kept perfect time. But one measurement cannot silence every question. We need more events, more mergers, more signals that carry both gravitational waves and photons. Each cosmic collision becomes another stopwatch, another line of evidence. Scientists are building networks of detectors across Earth. LIGO, Virgo, KAGRA, forming a synchronized array that listens to spacetime from multiple points. When a wave washes across the planet, we track its arrival at each site, triangulating its path like lightning strikes measured across continents. The time differences are impossibly small, milliseconds across thousands of kilometers, but each is a clue, a data point, a part of the unfolding story. With every detection, we narrow uncertainty. We tighten the error bars. We refine models of propagation, dispersion, redshift, cosmic drag. And still, we hunger for more. Because as powerful as LIGO is, it is only the beginning. It hears the universe, but faintly, like one ear pressed against a distant wall. To truly test gravity's speed across cosmic scales, we need instruments larger than continents, more sensitive than mirrors, more patient than generations. We need detectors in space where ground vibration cannot touch them. We need pulsar timing arrays, vast networks of spinning neutron stars acting as galactic clocks, where gravitational waves stretch the timing between pulses across tens of thousands of light years. Each pulsar becomes a metronome, And if a gravitational wave brushes past us, the timing shifts. Not by seconds, by nanoseconds. With enough pulsars, enough time, we could measure delays so small they reveal whether gravity's speed remains unwavering across the entire universe. And here tension sharpens again into anticipation. Future detectors will not just confirm Einstein. They could expose cracks he never saw. LISA, the Laser Interferometer Space Antenna, will unfold millions of kilometers wide in orbit, listening for low-frequency waves from supermassive black holes. Pulsar timing arrays will map gravitational tremors across the Milky Way itself. Third-generation detectors like the Einstein telescope and Cosmic Explorer will catch events from the dawn of the universe, waves stretched thin by cosmic expansion. If gravity's speed ever falters, even by the tiniest margin, these instruments will find it. If propagation changes over distance, frequency, or environment, the waveform will betray it. If dark energy or extra dimensions influence gravitational waves, timing deviations will emerge like fingerprints. So the mystery deepens, not softens, and we press forward with new tools, new ears, new precision. We know gravity travels at sea where we've measured it, but we have not yet tested every regime, every scale, every condition. The next era of detectors will decide whether relativity stands uncracked, or whether gravity hides something stranger, something faster looking, something beyond Einstein's reach. Which brings us naturally to what comes next. Next-gen detectors. Machines that may hear gravity differently, more clearly, deeply enough to challenge everything we think we know. What if LIGO was only the first whisper? A child's stethoscope pressed to the ribs of the cosmos. And the next generation of detectors will hear the universe like thunder rolling across creation. This is where the mystery deepens again. What comes after LIGO? Because if gravity truly travels at light speed, the more precisely we listen, the more that truth should harden and sharpen into certainty. But if gravity ever behaves differently, even for a fraction of a second, then stronger detectors could catch the slip. They could expose subtle deviations in timing, tiny mismatches between gravitational waves and light, minute shifts in frequency as ripples stretch across billions of light years. And right now, humanity is building the tools to test gravity with sensitivity that LIGO could only dream of. Detectors that will be bigger, quieter, more precise, listening not just to nearby black holes, but to the deep, ancient pulse of space-time itself. Start with LISA, the Laser Interferometer Space Antenna. Instead of mirrors suspended in the ground, LISA will float in space. 3 satellites separated by millions of kilometers, exchanging laser beams across the void. Free from Earth's tremors, free from seismic noise, free from wind, trucks, footsteps, shifting soil, LISA will listen for waves thousands of times lower in frequency than LIGO can detect. These are waves from supermassive black holes merging, from galactic binaries, from gravitational murmurs left over from the early universe. If gravity ever deviates from light speed over long distances, LISA could measure the delay with unprecedented precision. A wave traveling slower than expected would arrive sagging, red-shifted beyond prediction. A wave traveling faster, or through a shortcut in warped geometry, might reach us early, off phase by microseconds after crossing millions of light years. A deviation that small is invisible to LIGO, but not to LISA. Then scale up, not in orbit, but across the galaxy itself. Pulsar timing arrays use neutron stars as cosmic clocks, more accurate than any machine humans can build. Pulsars spin like lighthouses, firing radio pulses across space, with a rhythm so precise that a gravitational wave stretching spacetime by the width of an atom across a light year could alter their timing. If gravity's speed shifts even slightly over cosmic distances, pulsar arrays will pick it up. They won't just detect waves. They'll track how those waves age, how they stretch, how they disperse. A gravitational wave traveling slower than light across billions of years would lag behind its electromagnetic siblings. A wave slipping through extra dimensions could arrive distorted. A wave traveling through warped bulk geometry could appear to take shortcuts the way light never could. Pulsar timing arrays won't listen for moments. They'll listen for decades, building datasets so enormous that even a microscopic deviation becomes measurable. And then come the monsters, Cosmic Explorer and the Einstein telescope, future ground-based observatories up to an order of magnitude more sensitive than LIGO. They will catch thousands of mergers per year, mapping gravitational propagation with millisecond precision. They will build stat sheets of spacetime itself, tracking the universe's heartbeat across epochs. If gravitational waves ever outrun light, even in rare edge cases, even near black holes, even across expanding voids, these megadetectors may be the first to see it. If the speed limit cracks, even by a hair, we may have instruments strong enough to measure the fracture. And if not, if every signal arrives exactly within light speed tolerance, then Einstein's ceiling holds. The law stands, but tension doesn't fade with better instruments. It sharpens, because with every leap in sensitivity, we inch closer to the unthinkable. What if one day we find superluminal gravity? What if one wave breaks formation, arrives early by a measurable margin? What if Lisa hears a merger before light does? What if a pulsar timing array reveals a ripple traveling ahead of photons? It wouldn't just challenge relativity, it would detonate it. It would rewrite causality. It would force physics to confront a truth it has never been comfortable with. Either gravity can outrun light, or space-time itself can fold reality into shortcuts we haven't yet understood. So now, the hook turns razor sharp. If we ever detect gravity arriving sooner than it should, what would that mean? Would physics bend or break? Would causality unravel? Or could the universe have loopholes that mimic faster-than-light behavior without truly violating relativity? That's where we go next. Into the strange hypothetical realm where gravity exceeds light speed, and reality, as we know it, fractures at the seams. If gravity ever arrived early, even once, the universe would tremble with the implications. Faster-than-light gravity wouldn't just bend the rules of physics, it would shred them. Imagine a gravitational wave beating photons to Earth from a distant merger, or an alteration in the Sun's mass affecting planetary orbits before the light from that change reached us. The moment gravity outruns light, causality collapses. Cause and effect unpair. Time no longer flows in one direction. Information could move backward through space-time, like water running uphill. A signal could reach its destination before it is sent. A warning could prevent the very event that triggered it. The universe becomes a hall of mirrors where outcomes loop without origin. An impossible world where logic folds into paradox. If gravity exceeded light, relativity must be discarded. The spacetime geometry Einstein gave us, elegant, self-consistent, verified by lensing, waves, orbits, clocks, would crumble. Every prediction matched by observation would need rewriting. Cosmology, black hole theory, quantum field models, all rebuilt from scratch. Faster-than-light gravity doesn't just change physics, it rewrites the foundation beneath reality. And the tension tightens because theoretical frameworks can be rebuilt, but only at a cost. If gravity was superluminal, it would need its own timing structure, its own causal lattice, distinct from light. Spacetime could no longer be one fabric. It would be two maps layered at different speeds. Mass could influence across the cosmos faster than messages, faster than photons, faster than time itself. Imagine navigating a universe where gravitational information arrives ahead of electromagnetic information. Signals diverge, predictions fracture, observations lose their coherence. Gravitational waves would be advance warnings of cosmic events. Supernovae we feel before we see, black hole mergers detected through curvature before radiation escapes. Telescopes would always be late. Every flash of light would tell a story already known through gravity's echo. But physics isn't just about knowing, it's about consistency. If gravity races ahead, the universe becomes inconsistent. Closed time-like curves, loops where cause and effect chase themselves, would emerge naturally. Faster-than-light influence allows, in principle, time travel. Not fiction, serious relativity math. If information outruns light, there exists a reference frame where it travels backward in time. One observer sees an effect precede its cause. The universe breaks its own logic, and nature, so far, refuses to let that happen. Still, what if apparent superluminality were possible? Not real speed, but something that looks like it. Perhaps gravity isn't truly outrunning photons. Perhaps it's using shortcuts that light cannot access. Perhaps extra dimensions fold the distance. Perhaps space-time curvature creates tunnels, geodesics shorter than light can travel. Maybe gravity doesn't break the limit. Maybe it bypasses it. Brain-world shortcuts, bulk leakage, wormhole tunnels, quantum tunneling. Theoretical loopholes exist, each hinting that speed might be an illusion. What looks like superluminality could really be topological trickery. Gravity slipping under the floorboards of space rather than sprinting across it. If that's the case, then faster-than-light gravity wouldn't destroy causality. It would reveal a deeper structure beneath it. A metageometry, a hidden architecture. So the real question becomes sharper. Could gravity appear superluminal without actually violating relativity? Could quantum fields, exotic space-time curvature, phase velocities, or propagation through extra dimensions produce the illusion of FTL behavior while preserving causality at a fundamental level? This leads us to loopholes, edge cases where waves can seem faster than light, where information appears ahead of prediction, where velocity is not the same as information transfer. There are analogies in optics and plasma physics where phase velocity exceeds c without breaking anything fundamental. If something similar exists for gravity, if spacetime allows apparent superluminality, then we must explore where those illusions occur and how to recognize them. And that brings us to our next chapter, apparent superluminality, where things look faster than light but aren't, and where we test whether gravity could ever join that strange category. Sometimes speed is a trick of perspective. A shadow crossing the moon can race across craters faster than light, even though no particle travels that fast. A laser dot sweeping across a wall can jump from one end to the other faster than photons can move, because the spot moves, not the beam itself. In physics, illusions of velocity are everywhere. They tempt us, tease us, suggest impossible speed while obeying every rule beneath. This invites a new mystery. Could gravity ever appear faster than light without actually breaking relativity? The idea sounds impossible until you realize that phase velocity, the speed at which the shape of a wave crest moves, can exceed c in plasmas, metamaterials, and even in light passing through certain media. The peaks in a waveform can shift faster than light, even though no information rides with them. Nothing meaningful outruns causality. Nothing usable transmits ahead of the limit. The wavefront, the first moment of arrival, always travels at c or slower. Nature allows illusions of speed so long as no message, no cause, no information travels in the cheat lane. So what if gravity works the same way? Imagine gravitational waves propagating through curved spacetime, the way light moves through glass or plasma. Their group velocity, which carries energy and information, must remain bound to light speed. But their phase or pattern of oscillation could shift differently. Over cosmic distances, gravitational waves stretch, redshift, distort as space expands beneath them. Peaks and troughs slide like waves on a drumhead pulled tight. In warped regions, near black holes, through curved intergalactic channels, across bulk dimensions, the patterns might travel in such a way that the crests appear to move ahead of schedule. The universe could fool us into thinking gravity arrived early when no actual signal had outrun light at all. The illusion would be subtle, delicate, encoded in waveform structure, detectable only by instruments sensitive enough to separate group from phase. LIGO catches entire mergers. Next-gen detectors might catch structure, the fine detail. And if one day we notice a pattern where the crests outrun the troughs, where the oscillation outpaces expectation, we may confront an apparent superluminality, not in violation of relativity, but permitted by it. Imagine measuring two gravitational waveforms from twin black hole mergers. Both traverse cosmic voids, but one travels through a dense cluster, a region of warped curvature and dark matter. The other crosses emptier space. Light from those regions might scatter or bend differently. But if gravity's waveform shifts through curved topology, its phase portrait might arrive slightly altered, slightly offset. Not because gravity is faster, but because the path is stranger. Just as sound travels faster through steel than air, gravity might propagate more efficiently through some space-time geometries. Yet even so, causality stands. Information stays locked to light speed. The universe lets the silhouette run faster than the object casting it. And so, no paradox blooms. No timeline breaks. Apparent superluminality becomes a clue, not a violation. And here we hit a new frontier. Can we simulate this on Earth? Build analog gravity systems, labs where fluid flows mimic horizons, where Bose-Einstein condensates imitate space-time curvature, where phonons travel like gravitons through emergent structure. In such analog systems, acoustic horizons have been created. Black hole mimics where sound waves cannot escape. In these experiments, phase waves can outrun group waves, ripple patterns can exceed emergent speed limits, and yet no information escapes faster than allowed. These are gravity's training grounds, model universes in miniature. If we study them deeply enough, we might see how gravity could look superluminal without actually crossing that threshold. We could test whether shortcuts exist, not by breaking the universal speed limit, but by bending the medium itself. So the tension rises once again, because if gravity's speed can be imitated in a laboratory, we may uncover behavior we've never observed in space. Maybe some wave structures will appear to leap ahead of constraints. Maybe causal limits will emerge naturally from emergent geometry. Maybe, by studying analog black holes, we unlock clues about quantum gravity that no telescope can reach. And that sets the stage for something bold, using earthbound physics to explore cosmic rules. But the true mystery lies just ahead. If analog gravity can mimic curvature and speed behavior, then perhaps spacetime itself isn't fundamental. Perhaps it emerges from deeper interactions, like fluid flow emerges from atomic motion. That possibility reshapes the question entirely. What if spacetime is not a stage, but a product? If so, speed limits might be properties of emergence, not absolutes of nature. And that leads directly into our next chapter: analog gravity experiments, where scientists create artificial black holes, watch horizons form in the lab, and probe how ripples behave when reality is rebuilt from the ground up. Gravity feels untouchable, a cosmic actor too vast, too elusive, too deeply tied to spacetime for human hands to manipulate. We can drop apples and watch them fall, but we cannot bend spacetime like clay, cannot conjure a black hole in a laboratory, cannot shake the universe hard enough to make it ring. Or so it seems. But a new mystery has emerged in the last 2 decades. What if gravity can be imitated, not using stars or supernovas, but with fluids, sound waves, condensed matter systems here on Earth? What if space-time curvature has an analog, something we can simulate, shape, experiment with directly? Instead of listening to the universe, we could recreate it in miniature. That possibility electrifies physicists, because if we can imitate gravity, we can test it, provoke it, push it until it shows us secrets the cosmos keeps hidden. And that is where analog gravity experiments enter the story. Laboratories where scientists mimic horizons using flowing water, Bose-Einstein condensates, superfluids, even optical media where light behaves as if trapped by a gravitational well. These aren't metaphors. They are real experiments where horizons form, where waves fall inward and cannot escape, where space-time-like behavior emerges from material physics. Imagine a river flowing toward a waterfall. Upstream, ripples travel freely, but near the drop, the current speeds beyond the wave velocity, and once past that point, ripples can no longer swim against the flow. That region acts like an event horizon, not for light, but for sound or surface waves. Physicists build systems like this intentionally. Water, black holes in circular tanks, superfluid vortices where excitations are dragged inward like photons near a singularity. In these setups, waves can stretch, redshift, compress, just like gravitational waves crossing curvature. Acoustic horizons trap phonons the way real horizons trap photons. And when these artificial black holes ripple, we can watch exactly how their signals propagate. No supernova required, no billion-year time of flight. We get gravity-like behavior in real time. We can measure wavefront speed, phase velocity, dispersion curves. We can tweak the medium, change its density, tune its geometry, and see how the gravitational analog responds. Something impossible to do with real spacetime. These experiments turn the question on its head. We aren't measuring gravity anymore. We're modeling it. And here tension rises sharply because analog gravity has already delivered glimpses of the impossible. In Bose-Einstein condensates, tiny quantum fluids chilled near absolute zero, scientists have observed behavior resembling Hawking radiation. Quantum particles emerging near an artificial horizon. Waves inside these systems sometimes appear to outrun their group velocity. The phase of a ripple can race ahead like a shadow crossing the moon, giving the illusion of superluminal propagation even though no information rides with it. Nothing violates relativity, yet the imitation reveals how a system can appear faster than its fundamental limit. The lab becomes a playground for cosmic rules. If waves in a simulated spacetime can distort, morph, redshift, even mimic horizon physics, then maybe gravity in the real universe has similar room for nuance. Behaviors too subtle to detect at interstellar scale, but observable in controlled analog systems. What we learn from ripples in a ring of superfluid helium could one day illuminate ripples in spacetime across billions of light years. Picture this: a gravitational wave analog in a quantum fluid. A disturbance is triggered at one point, and waves propagate outward. If we alter the geometry of the medium, tighten it, stretch it, create curvature, the signal changes speed relative to observers inside the analog frame. Not breaking light speed, but modifying the effective propagation through topology. This is the kind of system that might show us how gravity could appear faster without ever truly breaking causality. Multiple analog labs have already produced horizon effects. Flowing water, black holes in Vancouver, laser-induced horizons in optical media, phononic event horizons in ultra-cold condensates. We are building worlds within worlds, little universes where scientists can poke gravity with a stick and watch it respond. If any hidden behavior exists, dispersion at scale, frequency-dependent propagation, quantum leakage across horizons, analog gravity could reveal it. And here is the hook, cutting deep. If we can imitate gravity, we might uncover behaviors our telescopes cannot yet see. Maybe under certain geometries, waves distort faster than expected. Maybe quantum horizons behave differently than classical ones. Maybe information rides spacetime in emergent layers, not in a single smooth continuum. Analog models may show us gravity not as a law of nature, but as a phenomenon that emerges from deeper mechanics, opening the door to a far more radical possibility. Spacetime itself may not be fundamental. It may arise the way sound arises from molecules, the way fluid flow emerges from atoms. If so, gravity's speed isn't a constant. It's a property of emergence. Shift the underlying structure, and the behavior may shift too, which takes us directly into the next frontier. If gravity emerges from microscopic information, what does that make space-time itself? Something built? Something derived? Something that could break under extreme conditions? Next, we step into one of the most revolutionary ideas in modern physics: the emergence of space-time, where gravity may not be fundamental at all. If gravity isn't a force, and space-time isn't a stage, then what if both are consequences of something deeper? This is the next and most destabilizing mystery. What if space-time is not fundamental, but emergent? Not a built-in feature of the universe, but a collective phenomenon formed from something microscopic, like temperature emerges from vibrating atoms, or pressure emerges from molecular collisions. In this view, space-time is not the foundation, it's the surface foam, the large-scale behavior of hidden degrees of freedom beneath. Gravity then wouldn't be a field to measure, but a byproduct of information flow, entropy, and statistical behavior. Just like fluid dynamics tells us nothing about individual water molecules, general relativity may describe space-time beautifully without revealing what space-time is made of. This idea doesn't weaken Einstein, it reframes him. GR becomes thermodynamics, not mechanics. Gravity becomes the thermal gradient of the universe, not a primary interaction. And here the tension begins to vibrate, like a string pulled too tight. If space-time is emergent, then gravity doesn't need a particle or a wave. It would arise automatically from microscopic states scrambling to maximize entropy. Several theories, from entropic gravity to ADS/CFT duality to tensor networks, propose exactly this. Space-time curvature emerges from the distribution of information. motion through spacetime is actually information rearranging itself. Distance is defined by entropy gradients, not by meters, and gravitational attraction may simply reflect the universe moving toward more probable configurations, like a drop of ink spreading in water. In such models, speed limits aren't arbitrary rules, they're emergent constraints within the macroscopic behavior. Just as sound has a speed limit in air, gravity may have one in spacetime. But here's the catch: if spacetime is emergent, could the microscopic substrate allow faster-than-light behavior beneath the surface? If quantum bits of spacetime interact differently, if information in the underlying network moves freely while the emergent geometry restricts signals, then superluminality could exist underneath spacetime without violating causality within spacetime. Picture gravity not as a field, but as the average behavior of trillions of interacting microstates. A collective pulse of information the way waves are collective motions of water molecules. A single water molecule can move faster than the wave it contributes to. So could quantum bits of spacetime transmit effects faster than emergent gravity allows? Some theoretical constructs suggest yes. Entanglement already hints at instantaneous correlations, even if no usable information travels that way. Holographic duality suggests three-dimensional spacetime maps onto two-dimensional information surfaces, meaning distances, speeds, even geometry could be illusions of emergence. If the spacetime we experience is a coarse-grained phenomenon, then the speed of gravity might not be fundamental. It might be a phase speed, not the speed of information itself. Under the right extreme conditions, near singularities, inside black holes, at the Planck scale where geometry dissolves, emergent constraints might fail. And if the emergent layer falters, speed limits could break beneath physics as we know it. This is where the mystery bites down hard. What if the universe has two speeds? One for emergent spacetime, the one we call c, and another for the underlying information. Substrate, silent, invisible, faster? We may never know unless we can model spacetime emergence the way we model turbulence or superconductivity, as a macro behavior built from micro rules. And if emergent gravity is real, analog experiments become more than curiosities. They become maps. They show us how macroscopic wave speeds arise from microscopic freedom. They reveal how an emergent system can follow strict limits while hiding deeper motion under the surface. And they suggest something daring. If spacetime emerges, then speed limits emerge, and emergent limits can be bent. Which leads us to the next inevitable question. If entanglement operates instantly but carries no usable signal, could gravity somehow connect to quantum information? Could entanglement be the thread weaving spacetime together, the hidden substrate from which geometry, distance, and speed arise? Next, we move into information and entanglement, where particles seem to influence each other instantly. And we ask whether gravity might be secretly tied to quantum information flow itself. Entanglement breaks our intuition in the cleanest, sharpest way possible. Two particles are prepared together, separated by miles or light years, yet when one is measured, the other reacts instantly. No delay, no propagation, no waiting for light-speed communication. It's as if reality updates in both places at once. Einstein hated it. Spooky action at a distance, he called it, because nothing else in physics behaves this way. Meanwhile, relativity stands firm, insisting nothing can transmit information faster than c. And strangely, both views are right. Entanglement correlations appear instantly, but no message, no controllable signal, no usable information travels in the exchange. You cannot choose an outcome on one particle to send a message to the other. There is influence, but not communication. Connection, but not causality violation. Entanglement is a ghostly link across space that doesn't move through space at all. That tension pushes us to a breathtaking question. What if space-time itself is woven from entanglement? Some modern theories suggest exactly that geometry emerges from quantum information the way a hologram emerges from encoded patterns on a surface. In this picture, gravity is not a force, not even curvature. It's the statistical result of how quantum bits connect. Distance becomes the number of entangled links between regions. Mass warps spacetime by altering entanglement structure. And speed limits emerge from how fast entanglement patterns can change, not from how fast something travels through space. If entanglement is the scaffolding of reality, then gravity may not need to travel. It may simply update, like nodes in a network restructuring. But here's where danger creeps in. If entanglement is instant, could gravity inherit some trace of that instantness? Could changes in quantum information ripple through the web beneath spacetime faster than classical curvature allows? If so, gravity's propagation might only appear limited to light speed, a consequence of how entanglement resolves into large-scale geometry. Under extreme conditions, near singularities or quantum horizons, the emergent fabric could glitch, allowing deeper levels of information to move differently. Not faster than light signals, but structural shifts that classical spacetime interprets as gravity behaving strangely. So the mystery sharpens. Relativity protects causality on the surface, but the quantum layer beneath might not play by the same rules. If gravity emerges from entanglement, then understanding how information flows and how it updates becomes the key to understanding why gravity travels at sea and whether it ever could deviate. Which leads naturally to our next step, the holographic principle, where the universe may not be 3D at all, but a projection coded on a distant boundary of reality. What if everything, space, time, gravity, galaxies, you, is not truly three-dimensional, but the projection of information stored on a distant two-dimensional boundary? This is the holographic principle, one of the boldest ideas modern physics has ever produced. It began with a puzzle buried inside black holes. The more material you drop into one, the more its entropy grows. But not with volume, only with surface area. A black hole's information capacity scales with the area of its event horizon, not the space inside. Something profound is implied there. Information in our universe may reside not within space, but on its edges, like a cosmic hard drive written across the surface of reality. If that's true, then what we call space-time might be just a holographic reconstruction, an emergent 3D experience generated from 2D quantum data. And if gravity arises from the way that surface information organizes, then gravity isn't fundamental at all. It's the byproduct of how entanglement patterns arrange themselves across the boundary. Here the tension tightens. How does something as smooth and continuous as space-time emerge from discrete information encoding? The holographic principle suggests that the geometry of the universe, its curvature, its expansion, its gravitational wells, isn't primary. It's compressive logic. Entropy defines geometry. Mass warps space not because of a force field, but because it changes the information gradient on the holographic surface. Gravity, in this interpretation, is entropic flow. Objects move toward regions of higher information density the way heat moves toward equilibrium. Einstein's equations still hold, but their meaning shifts. Curvature isn't a structure, it's a story told by information. light speed limits become constraints on how fast that information can update. And suddenly, gravity traveling at sea makes sense, not as a physical velocity, but as a rate of information refresh in the holographic fabric. If the universe is a hologram, then spacetime is like a rendered simulation, and gravity is the computational delay that emerges when information rearranges across the surface. Nothing breaks relativity, because the information beneath it still respects causal structure. Propagation isn't about waves in space, it's about how fast the holographic boundary can recode reality. Light speed becomes the maximum rate of update, not a speed in space, but a limit on what the holographic processor can compute. This perspective could explain why gravity never outruns photons. The universe won't allow information to refresh faster than c. Yet, hidden inside this logic, another question flickers like static beneath a screen. If gravity emerges from information, could edge cases in that encoding produce anomalies, glitches, rare configurations where updates propagate differently? Which brings us to our next frontier. If the holographic principle shapes the universe, what patterns should we see on the cosmic web itself? The vast filament network connecting galaxies across billions of light years? On the grandest scale, the universe isn't random, it's patterned. Galaxies don't scatter like sand tossed into the wind. They form a cosmic web, vast filamentary threads of matter stretching across billions of light years, connecting clusters like nerves in a brain. Dark matter forms the scaffolding. Gas flows along its veins, stars spark where filaments knot. This structure didn't appear instantly. Gravity sculpted it over eons, pulling, clustering, merging, weaving the universe into its great lattice. What begins as quantum fluctuations becomes superclusters. What begins as a whisper becomes architecture. And yet, a mystery hangs over that structure like a silent question. Does gravity shaping the cosmic web always propagate at the same speed we measure locally? Because if gravity ever acted even slightly faster or slower at vast distances, the web would not look like this. Filaments would be thicker or thinner. Voids would widen differently. Galaxy clusters might form sooner or later. The entire large-scale universe is a fossil record of gravity's behavior. The tension grows. If gravity weakened or propagated slower across cosmic scales, galaxies would drift apart before clustering. If it were stronger or faster, structures would collapse too quickly. The cosmic web is a balance beam, precision sculpted by time. Its existence confirms gravity's long-term consistency, yet doesn't eliminate the possibility of subtle deviations still hidden from us. Perhaps slight changes in propagation speed would alter structure in ways nearly imperceptible unless we look deeper, map more finely, simulate with higher resolution. Some cosmologists already test these ideas with modified gravity models, adjusting how influence spreads over billions of light years to see how filaments respond. A tiny change in speed could shift the fabric of the web. The question now burns: did gravity behave differently in the early universe? And if so, would we detect that imprint today? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.